I want at least one truly stupid question from each of you. Okay, so wonderful, weird world of general relativity. You have black holes, bending of light, and tidal forces, which makes the rings on Saturn. We're going to see an astronaut falling into a black hole. It's an animation, it's not a real astronaut. And watch what tidal forces do to him. General relativity is important around immense masses, like the sun, like galaxies. And the basic idea is really simple, but it's not at all easy. And the main thing is acceleration. When I push you, you feel a force against your back as we go off. And you remember that when you're in a car. All right, now walk and I'm going to swing you around and I'm accelerating you in. There you go, you're being accelerated. That's why you went in a circle. Acceleration due to gravity. And the ball drops. You can have acceleration with a rocket ship in outer space. It's way out in the middle of nowhere. If it's accelerating, the ball will stay in place until the rocket catches up with it. Ball doesn't move, but if you were inside the rocket, it would kind of look like it's moving, right? This time, we're going to move with the rocket as it goes faster and faster. Here we're going to have two pictures. It's like we took two movies and we're going to play them side by side. Same acceleration. Here you're in a room, didn't have any windows, but you might be on a spaceship, Starship Enterprise or something, and you'd be in a room, it'd look exactly the same inside. You can't tell, you can't look outside. Could you tell the difference as to which of these two situations you're in? Oh boy, the ball drops exactly the same. So if you're inside, do you think you could tell the difference? Anybody? General relativity. You are now in the world of general relativity with that very simple thing, principle of equivalence. And Einstein's principle of equivalence just says that this is equivalent to that. Rocket is equivalent to gravity. And now we're ready to see how gravity bends light. So what we have here is we have a little pulse of light, but on, off. So there's a little pulse of light on, off, and it's going to travel on this. I have a blue line here on the rocket just so you can keep track of where the dot is as it goes across. It'll cycle a couple of times. Okay. Oh. So if you're out here, you can see that this ball is always at the same level. It never moved relative to outer space here. But inside, if you look at that, it looks like the path is curving. Look.
So, in this little cartoon thing,
yeah.
Is the light really bending, or is it just staying the same? The rocket is moving up.
So that's a good question. If we have acceleration in a rocket and acceleration due to gravity, so we have the two cameras played side by side, we're going to watch the light come across here, and we'll watch the ball drop. And it goes back to your question. Same. Remember, you can't tell the difference if you're inside. So you see it curving here, and if you're in here, you see it curving. It acts curved. This is weird. And this is the thing that Einstein came up with. If you have the sun is a huge mass. So if you had a star over here, the light comes here and it's trying to go straight, but it's curved as it goes by the sun. Oh, this is what he predicted. During an eclipse, the moon blocks the sun out, and you can see the bending of the light, and so the position of the star now looks like it's out here somewhere, not here, but there. There were a couple of stars here, and a couple here, and there were a bunch more. This light is bent by just the right amount. It's bent more here, less there. Everybody believe that masses can bend light, that the space is curved around a big mass? If matter is dense enough, the gravitational force is so great that light can't even escape. Now, the Schwarzschild radius, if a mass is smaller than its Schwarzschild radius, it will be a black hole. If you could make the entire Earth collapse into this diameter, it would be a black hole. An astronaut sitting here, suddenly the Earth collapsing down there to this size. When it gets to about 10 kilometers to 1 kilometer, the force at his feet, the gravitational force, is so much stronger, and he will stretch out. Now, his feet are ripped off, then his legs, because of the strength of gravity, and he is just ripped to pieces. Finally, his head comes off. And he's getting stretched, as you said, stretched out longer and longer and longer, and there he goes. And that's what will happen You now know more about the effects of acceleration, whether it's gravity or rockets, more about the effect of acceleration on light, than the very, very best educated people did 100 years ago. And you saw the basic idea is simple, it's not easy, and a secret of life. Everything you learn in school, even in universities, is simple. It's not always easy, and sometimes there's an awful lot of it, like an automobile. But basically, if it's taught in school, it has to be simple, because if it wasn't simple, nobody in the entire world would understand it. So the trick is to find the simple clue, and you can do it. Thank you.